Hello and welcome. In this video entitled A Simple Explanation of Infrared Spectroscopy, I will begin by considering infrared radiation itself, and I'll explain how its wavelength is converted to handier wave numbers for use in infrared spectroscopy. Next, I'll consider the characteristics of covalent bonds that facilitate infrared spectrochemical analysis. I'll then move on to briefly outline the inner workings of a typical infrared spectrometer. Finally, I will show you a number of different infrared spectra and acquaint you with the 2 different regions and 5 different zones used in the analysis. So infrared spectroscopy is one important analytical tool or forensic tool used in chemistry. Think of fingerprinting, where each individual has his or her own unique set of fingerprints. And what we do is we look in detail at characteristic patterns within the fingerprint in order to identify the fingerprint or match the fingerprint with the individual. In analysing the fingerprint, so-called arches, loops and whorls will be examined. Now when we turn to infrared spectroscopy, again we have a kind of fingerprint, but this time it takes the form of a graph like this. And here, instead of looking for arches and loops, we're looking at where these so-called troughs or peaks appear relative to the x-axis. Now let's consider where infrared radiation appears within the electromagnetic spectrum itself. So you'll be aware that electromagnetic radiation takes the form of waves like this. As I've drawn the electromagnetic spectrum here, you've got waves of very short wavelength to the left, and those with the shortest wavelength are called gamma rays. Next you have waves of shorter wavelength, and we have the X-ray band of the electromagnetic spectrum, followed by UV, then visible light, and to the right of visible light and of longer wavelength and lower energy we have infrared, then microwaves and radio waves. Up there at the extreme left of the electromagnetic spectrum we have waves of very, very short wavelength, about 10 to the power of minus 16 meters. And at the beginning there of the radio part of the electromagnetic spectrum, waves have a wavelength of about 1 meter. So you can see that infrared is to the right of the visible part of the electromagnetic spectrum. So infrared is radiation of longer wavelength and lower energy than visible light. And that's the part of the electromagnetic spectrum clearly that we're using here in infrared spectroscopy. Next, let me take a moment to explain how we change wavelength in nanometers into so-called wave numbers in centimeters to the minus 1 or reciprocal centimeters. The infrared band of the electromagnetic spectrum stretches from, as you see there, 7.5 by 10 to the minus 7 up to 1 by 10 to the minus 3 meters. Let's convert that to centimeters. So you multiply by 100, so that's 7.5 by 10 to the minus 5 to 0.1 centimeter in wavelength. Now, let's see how we convert wavelength to wave number. Well, wave number is simply 1 over lambda, lambda being the wavelength. And the wavelength, however, has to be expressed in centimeters. So that gives wave number as 1 over centimeters, or centimeters to the minus 1, or reciprocal centimeters. So that means that the infrared part of the electromagnetic spectrum stretches in terms of wave numbers from about 13,333 to 10 reciprocal centimeters. Now, as you see here, the infrared band is divided into 3 different regions: the near, middle and far regions. Near infrared stretches from 12,800 to 4,000 reciprocal centimeters, middle 4,000 to 200 reciprocal centimeters, and far infrared from 200 to 10 reciprocal centimeters. It's the middle region that is most useful for the analysis of organic compounds using infrared spectroscopy. So the region 4,000 down to 200 reciprocal centimeters. Note that the larger the wave number, the higher the energy. Now getting into the nitty-gritty, let's consider the characteristics of covalent bonds that give rise to this type of analysis. That's how we'd normally represent a hydrogen molecule, two hydrogen spheres joined by a line or stick. It would be better, in fact, to represent the bond as a spring, because these covalent bonds, in fact, vibrate. They're constantly vibrating. If you look at the two molecules there, two lower molecules, you can see the spring is stretching in and out. The same can be used to represent, and should be used to represent, an oxygen molecule, but you'd need two springs because there's a double bond there. Or in the case of nitrogen, where we have a triple bond, two N spheres joined by three springs. I'm going to use the carbon dioxide molecule CO2 here to show you that molecules with covalent bonds are not necessarily active in infrared spectroscopy. So the carbon in CO2 is double bonded to oxygens on either side. And here in the bottom left hand corner you can see the bond stretching out and back in again. But there are different types of stretches and indeed bending actions in the molecule. Look at this molecule I've just drawn and you can see that it's stretching out more on the left than it is on the right. And look at this molecule. You can see the carbon dioxide molecule has moved from its normal linear shape to a bent shape. That's referred to as bending then, the others as stretching. In the bottom left hand corner, this is said to be a symmetric stretch. It's the bonds either side of the carbon are stretching out equally. There's an equilibrium there. As opposed to here, this is an asymmetric stretch. It's stretching more to the left than it is to the right. And this results in the molecule having a so-called resultant dipole. And the molecule must, in one of its vibrations, it must have a resultant dipole in order to be active in infrared spectroscopy. The bending action as well is going to be active because in view of its bent shape, the dipoles won't cancel, and that molecule in that particular bent state will have a resultant dipole. The hydrogen, oxygen and nitrogen molecules are homonuclear diatomic molecules with no electronegativity difference. So as a result, in none of the vibrations do we find a state with a resultant dipole. So those molecules are inactive in infrared spectroscopy. Let's now consider the energy changes that take place and which are used in infrared spectroscopy. I'm going to use the carbon dioxide bending vibration to illustrate this. As you see in the diagram, there's an energy difference between the two different states. In the linear state, we have the lower energy state, and when it bends, we have a higher energy state. So when the molecule undergoes bending in this fashion, it absorbs energy to enter into the bent state, and it does so by absorbing a photon of energy, in other words, a specific wavelength of electromagnetic radiation. It then returns to the lower energy state, and it does that by giving out exactly the same photon of energy. Within organic molecules, many of the bonds that we find have vibrations which have photons that fall within the infrared band of the electromagnetic spectrum. When we pass monochromatic electromagnetic radiation, that's to say waves of a specific wavelength, through an organic sample, if that energy exactly matches the energy of the vibration of bonds that are present, then energy will be absorbed, and so more of those specific vibrations will take place. But by the nature of vibrations, as the molecules return to the lower energy state, those photons of energy will be given back out again. And then as we scan across the infrared band of the electromagnetic spectrum, changing the wavelength or wave number of the wave, and therefore the energy of the wave, as the energy comes into resonance with specific vibrations that occur within the organic molecules, then we'll get energy absorbed. And as you'll see shortly, as energy is absorbed, this will produce the peaks in the infrared spectrum. And note that the intensity of the peaks produced in the infrared spectrum depend both on the change in the dipole moment of the particular bond undergoing vibration, and on the number of the specific bonds present in the molecule. So for example, the CH peak in octane will be more intense than that for methane, CH4. Just in passing, let me use what we've learned so far to explain, in part at least, global warming. The sun's energy, in other words solar energy, is used up in various ways on Earth, for example in evaporation and in convection. And it's reckoned that the net equivalent of around 70% of solar energy is radiated back into space in the form of infrared radiation. Now of this, about 12% of the 70% actually escapes into space, and the remaining 5 to 6% is trapped in the atmosphere. And you see here the carbon dioxide molecules will absorb infrared radiation for those vibrations, and the molecules will then return to the lower energy state and give out those photons of energy in all directions. Some of that energy will radiate on up into space, while others will radiate back down to Earth again. Methane is also a greenhouse gas. It's produced where we have vegetation underwater. So, for example, from the paddy fields in China, from bogland in Ireland. And again, the same sort of thing is happening here. The methane molecules will absorb photons of infrared radiation. Those molecules will then return to the lower energy state and give the energy out in the form of photons, some of which will be redirected back down to the Earth again. And remember as well, water vapor is a greenhouse gas because water molecules are infrared active. Next, let me show you some animations that I've prepared to illustrate these types of vibrations found within molecules. I begin here with a water molecule. The blue represents an oxygen atom and the red's hydrogen atoms. What type of vibration do you see here in the water molecule? This is of course the symmetric stretch of the OH bonds. Occurs around 3,585 reciprocal centimeters with a relatively small intensity of about 0.17. This is the asymmetric OH stretch. Occurs around 3,506 reciprocal centimeters and has a much greater intensity of around 1.0. And next, this is the OH bending. Occurs around 1,885 reciprocal centimeters with a relatively small intensity of 0.15. And there are other vibrations that we see in more complex molecules. Here I'm looking at an amine such as methyl or ethylamine with its NH2 group. This is referred to as rocking, as you see. And next we'll consider a type of vibration called wagging. You see it occurs in the fingerprint region, so it's less useful for infrared analysis. And lastly, I'm trying to represent what's called twisting here. I'm not sure it shows it very well. But if you think of your two hands up in the air and you twist your body back and forth and how your hands would move, that's what you get. Okay, now I want to take a look at how the bond strength and the masses of the atoms bonded affects the energy of the vibrations of the bonds. In the spring analogy, you can see there that weaker bonds are best considered to be like a spring that is less tightly wound. And of course, bond strength decreases from triple to double to single, so you can represent that in the springs with less coiling. And pause and take a look at those representative examples. So again, hit the pause button here and look in yellow. Multiple bonds have higher wave numbers. With heavier atoms attached, the wave numbers are smaller. Now let's take a look at what happens inside the infrared spectrometer. You can see the infrared source marked with a red sphere there, and light beams, identical light beams, are sent out in two directions then. You can see they are reflected off mirrors. One passes through a reference cell and the other through the sample cell. Next, if you focus on the chopper there that's spinning around, it has a transparent end and a mirrored end. The transparent end will allow light coming through from the sample cell to pass through towards that grating shown in blue, whereas the mirrored end will reflect the light coming from the reference cell towards the grating. So quickly alternating beams that are coming from, in one instance, the reference cell and then the sample cell pass towards the grating. The grating then selects out beams of monochromatic light, and we have alternating beams from the reference cell and the sample cell, which pass down to the mirror there below and through a fine slit, and finally to the infrared detector. And of course the infrared detector will pick up differences in the amount of light transmitted by the reference cell compared with the sample cell. In other words, where we have absorbance of infrared radiation by the sample, we will have a drop in transmission, and that will produce the peaks or troughs on the infrared spectrum. So we're now finally ready to take a look at these infrared spectra and learn how to analyze them. First of all, it's divided into two regions, as you see here. There's the functional group region, which is from 4000 down to 1500, and then there's a fingerprint region from 1500 down to 500. And the functional group region is further subdivided into 5 so-called zones of analysis, and I've color coded them here for you. Let's begin with the one furthest to the left, and it's been color coded in cream, as you see there. Now the peaks that we'll get in that region will be for the OH stretch of alcohols, including phenol, the NH stretch for amines and amides, and the CH stretch where we have an alkyne, a triple bond to a C followed by C to a H. And I've color coded the next zone of analysis green, and you can see there this is where we get the CH stretch, which is going to be very common of course in organic molecules. It appears at around 3000 reciprocal centimeters, and we also get a peak there, a broad peak for the OH stretch of our carboxyl group or carboxylic acid group, between 3000 and 2500 reciprocal centimeters. Next, color coded in blue, we get the C triple bond C and C triple bond N stretches between 2260 and 2200, as well as the CH stretch as found in an aldehyde, occurs between about 2900 and 2700. Then in lilac here we have the fourth zone of analysis, and this is where you get the C double bond O stretch. But then C double bond O is common to a number of different functional groups, and over to the extreme right corner there you can see that you get C double bond O in aldehydes, ketones, esters, carboxylic acids and amides, and you can see where those peaks will be found. Aldehydes between 1740 and 1690, ketones 1750 and 1680, esters 1750 and 1735, carboxylic acids 1780 to 1710, and the C double bond O stretch in amides 1690 to 1630. That leaves us then with the fifth zone of analysis within the functional group region, and in this region we get peaks showing up the C double bond C stretch for alkenes, as well as the CC bonds found in aromatic rings where we have a delocalized electron system. And that's the functional group region. We then have the fingerprint region, which I'll make reference to a little later. So I'm going to look at a number of different infrared spectra now and try to analyze, by looking at the peaks, what functional groups might be present in the molecules. You might like to pause in a moment and try to elucidate from where the peaks occur the functional groups present in this molecule. This is in fact ethanol, which has this structure. Can you see the OH there? It's a broad peak. That's the OH stretch. Where's the CH stretch? That's it there. So ethanol. Moving on to the next one, again you might like to pause and attempt to work out the functional groups present here. This is the ketone butanone, which has this structure. Can you see the peaks for CH, the CH stretch there, and the C double bond O of a ketone, which is between 1750 and 1680. On to the next one. Pause again, see if you can elucidate the functional groups present. This is ethanoic acid, which has this structure. Now the OH of the carboxyl group is broad, and there's the C double bond O stretch for the carboxyl group. You can see there it's between 1690 and 1680. Moving on to the next one, pause again, have a go. This is aminobenzene, which has this structure. So we should be seeing an NH stretch, that's it there. And the CC of the aromatic ring is in around there. And the next one, pause and have a go. This is an ester, ethyl ethanoate, and that's the structure. So we should have the CH stretch, that's it there in the green zone. And we've got a C double bond O present in the ester, and it should occur there between 1750 and 1735. Now let me give you one example of the use of the fingerprint region to distinguish between two different position isomers of propanol. Now here's the first one, propan-1-ol. You can see in the cream and green zones there the characteristic peaks for OH and CH stretches. And here's propan-2-ol. Now in the green and cream zones there, they are virtually identical. Where we can distinguish between these two position isomers is in the pattern of peak created in the fingerprint region. Computer analysis will certainly pick out the difference, and a trained observer will have no difficulty distinguishing between one and the other. So that's it, a simple explanation of infrared spectroscopy. Thanks for listening.